Now, the co-integration is saying that in the long run, your variables will converge. They will meet at a point. So when you perform the co-integration test on your variable, which is not stationary, and you happen to find that in the long run, they converge or they are co-integrated, then we say that the errors are corrected in the long run. So you go ahead and you estimate what we call the vector error correction model, which is the VECM. You can also decide that if your variables, even though at level, they are not co-integrated, if you found out that they are co-integrated at first difference, or a mixture of first difference and second difference. Mind you, I said the first difference is when you subtract the variable. Let's say you subtract 2020 from 2021, the difference. That is what we call the first difference. And then you realize that it is stationary at first difference. You can go ahead and perform the ARDR. The reason is the ARDR also includes a long run analysis. But when you go ahead and you still find that they are not even co-integrating in the long run, then you can go ahead and estimate what we call the vector autoregression model. Now, the vector autoregression model here includes the lag, the previous year in the model. That's why we call it autoregressive. So with this said, is anyone having a question here, or we can move straight into it? Okay, thank you. So I also brought in some other models. Hello.
No, sorry, please, can you try and slow down a little? It's like you are a bit fast.
Oh, so sorry for that. So if I was fast, what I'm trying to say is when you have time series data, first you perform stationarity test, which mostly it is the Dickens-Fuller test. And then you find out if your data is stationary at level, like they are not changing randomly. There is no trend. There is no seasonality in your variables. If the variables are stationary, you can go ahead and perform the regression. After you perform the regression, you can do what we call post estimation test. You test for the normality of the residuals. You test for autocorrelation. You test for overspecification of your model to see if you've not missed some important variables. You also test for heteroscedasticity. And once you've tested all those things, you can decide to go ahead and do what we call robust check of your models or your results. So to do that, there are two ways. You can change some of your variables. For instance, if I'm explaining FDI in my country, now instead of using FDI, I can decide to use maybe FDI inflow, which is just capturing a section of FDI. Or I can decide to use FDI, which came in after a certain period of time, or FDI, which came under certain assumption. So that will become my dependent variable. Another way is you can also use other models to explain or to conduct your analysis. That's why you see people conducting quantile regression after they've conducted normal regression, or maybe a median regression, a GARCH or ARCH model, and all those things. Now, when you perform the Dickens-Fuller and you realize that your data is not stationary at level, you can decide to make it stationary by transforming the data. Transforming the data, it's very simple. It's like you changing the unit of measurement. For instance, if my data is about millions of dollars, I can decide to find the difference, and then it becomes like a growth or a change. Or you can transform them into log forms. Sometimes when you do those transformations, it will work. If it doesn't work, you can go ahead and perform what we call co-integration to see if in the long run, the variables, the errors correct, and then they converge. Once you do that, it's either it's going to be yes or no. If you find out that the errors in the long run converge, then you can go ahead and perform what we call the vector error correction model, which indicates that the errors in your model correct in the long run or in the future. But if they don't, you can go ahead and estimate what we call the vector autoregression model. Alternatively, if the data is, your model is not stationary at level or at phase difference, you can go ahead and estimate the ARDL model, because the ARDL model also includes long run estimation. I hope this was slow enough.
Yeah, it's okay.
Yes, okay.
Oh, okay, thank you. So let me quickly go into STATA and then we come back. So let me launch my STATA. Since it's a recap and then we have just 38 minutes, some of the things I may be fast and then we can watch the video afterwards. But I hope I'll be slow. So we start with the data the lecturers gave us. What I'm trying to do is to just fill in some of the gaps and also pick up some challenges. So let me just suspend this. My data is in Excel form, so I'm supposed to import it. So Excel. And then I have to pick the data from where I stored it. Too slow. And the data we were given, I think we were given, I think data set 1. And I prefer to make the first heading as my labels. And then I can decide to use lowercase so I can type. Now, one thing before I even go into it, let me probably do this once and for all. Let me do import my data and then do this once and for all. Now, you realize that if we look at the data sheet the lecturers gave us, they gave us a data set, and I want us to see something here. Okay, so this is the data set 1. I'm going to open it in Excel quickly. Okay, so now if you look at the data here, this is a transformed data. This is a raw data. The raw data is what you mostly download. The raw data is what you mostly download from wherever you are downloading it from. Now, if you look at this, trade is in 24 point something. It can be in millions of cities or billions. Now, when you look at employment is having like, I think 1, 2, 3, 1, 2, 3. It's also in millions. But when you look at urban population, it's 27 point something. So you see, the units of measurements are not the same. Now, when you look at HDR, it's in the form of an index. So one thing mostly I would prefer to do is to transform all my variables in Excel. You can do them in STATA. So for instance, let's say I want to transform employment, real employment. So I can just go here, and this time around, let's say I want to take the log of the employment. So I can call this maybe log of employment, okay? And then here, I just put equal to the natural log, and then I select the variable, close the bracket, hit enter. So you see, I have transformed the measurement, the unit of measurement of the employment variable. And then I can just go ahead and do it for every one of them. Now, assuming I want to do what we call the growth in employment. For instance, I was giving level data, yearly data, but I want to do growth. I can go and subtract the previous year from the current year, and then I'll find the difference. That is what we call the first difference. So let's say that one is also going to be the difference of employment. And I can go ahead and say that the difference of an employment, since it is going to be a minus, the first year will be dropped. So it's going to be the current year minus the previous year. Hit enter. And that's going to give me the difference. I can even convert the difference to percentage. If I want to convert it to percentage, it can be simple as into bracket, the current year minus the previous year divided by the previous year, bracket close, times 100. And here I am doing what we call percentage growth. And that is it. You see, it is an increase of 2.3% from 1991 to 1992. So these are some of the transformations, and you are free to do them in Excel. So with this said, let me just close it, and then we go into our STATA. Now, I imported my data. The first thing I have to do is to have a fair idea of my data, to be sure I have the right data set in place. Now, I can start by browsing my data. I'm not sure if this thing is going to help being at the top. Sorry for that. Okay, so the first thing is I'm supposed to just check on my data. So to do that, you can go to data and browse, or you can click on this icon with the magnifying glass, and you'll be able to browse your data. Alternatively, you can just type browse, and then you see how your data set looks like. So if you look at what is here, it looks like I imported the untransformed data. That is what I imported here. So I can go ahead and transform the data. If I want to transform, I can use the command box, or I can just go to data, and then I go to create and manage data, and then I go to create new data. So from create new data, I can give the variable name of the data I want to create, the new one I want to create. Let's say I want to call it log of trade. I want to call it log of trade. Now you click on the create icon here, and then you go to the expression builder. Now this is a very simple one I want to create. So mostly it's just going to be like a function. So I go here, and then I can go to mathematical, where you have all this. So I'm looking for log. So this is logarithm. Double click to open the logarithm, change the x here, and put the variable you want to transform there. Oh, it's try. So you just type the name of the variable there, and you hit OK, and then you hit OK, or you can hit submit. So let's say OK. And you see we've generated the log of trade. So now we have a new variable, which is log of trade. So you can go ahead and do for the rest of them. Now, the first thing I said was we check if our data is stationary. Kindly hold on for me. So the first thing is we check if our variables are stationary. So let's go to statistics. Now you can go to time series, and then you come to test, and you can choose augmented decontroller unit retest. You pick one variable at a time, but then before you need to set the STATA to know that this is a time series analysis. So you pick the time variable, which in this case it is year. It's not panel data, so ignore this. And then you choose yearly. You hit OK. Now you choose the first variable, let's say trade, and then you hit OK. And now this is it. Now, if you look at here, it says that our variable is random walk without a drift. But another way you can also check to see if your data has a drift, has a trend, is to go to statistics, time series, okay? And then you go to graphs. From graphs, you can decide to plot a line graph. You can decide to plot a line graph. So let's go line. You just choose a variable you want to plot, accept, let's hit OK. So this is how our variable looks like. You see, it is not revolving around the mean. It goes up, it comes down, it goes up, and it comes down. So definitely we have a problem here. Please, any question up to this far?
Yes.
Okay. Now, when we perform the stationarity test, okay, and then we realize that the p-value is above 0.05%, then we know that we are in for trouble. So if the p-value is greater than 5% significance level, we conclude that our data is not stationary at level. We can go ahead and check for the other ones as well. So let's go back to statistics, and then we go to time series, we go to test, we go to augmented decontroller. This time around, we can decide to check for the employment variable, and then we hit OK. And then we also have this here. So we are going around and then we are checking. You know, the null hypothesis is that random walk is without drift. It's without drift. So since we are rejecting it, we know there is a problem with our variable. Okay, so we can decide to go ahead and transform our variables, but I'm not going to transform it since we already have a transformed version, and I've showed you how to transform your variable. So with that, I'm going to clean this screen, and then I'll bring in the transformed data. So let's go to File, and then I will import from Excel. I will browse, dataset 1. So I will import, change the worksheet because I have multiple worksheets, and then I choose transformed. I change here also to lowercase, and then I hit OK. So from here, let me quickly go into it again. So we can decide to also check for our other tests as well. So first, we need to tell STATA this is a time series data we are working with. So you go to statistics, time series, set up utilities, and declare data set to be time series. You choose the time variable, and then you choose the unit of measurement, which is yearly, and then OK. Kindly hold on, let's check. Mostly you check for the you transform your variables to put them in a particular unit or level. You standardize it. So let's assume for standardization purposes, sometimes when your variable has problems, let's say there is even multicollinearity and all those things, some transformation may help. And also when you transform some of the variables, it also helps get a better explanation. For instance, if your variables are in percentages, explaining it is very easy. You just say 1% increase in this causes 1% increase in this. But if you don't transform it, and assuming some of your variables are in dollars and some of your variables are in indexes, maybe 0.1, when you are explaining it, it's quite difficult. These are some of the reasons. How to know if your variable works with drift, or can you please explain that word again? Okay, so like okay, so I'll come back to the graph. If your data is not stationary, I think we went through this one. When the data is not stationary, you can perform co-integration, then you perform either a VECM, or you perform a VAR, or you can even perform the GARCH model. So these are some of the things. The specific data set, we are working with the one we were given earlier on from the lectures. Thank you. Is using a natural log the only transformation of the verb? No, please. As I was saying, you can take differences and they are also transformations. Sometimes you can even cause interaction, multiplying one variable by the other. They are also transformation. It's all about working around changing the unit of measurement, mostly that has to do with the transformation. Wage data, yes, it depends on the unit of measurement. You can transform any data at all. Sometimes if you have data, you need to calculate the percentage change. And then mostly when you use the difference or the change, it's most likely you're going to have a stationary kind of variable. Okay, with this said, let's go into the graph. Now, the graph is such that let's go to statistics. We go to time series. And then from the time series, we go to graphs. We go to line plot. We just want to have a pictorial view of whatever like we are working on. So here we want to check the movement of log trade. So you select that one. You can choose what to use, whether you want to use scatter, but line is easier to see. Then you click accept, and then you can click on OK. Now, if you look at the variable, this is how it is moving. It increases and then it falls. It increases and then it falls. So here, let's assume this is the mean. If you draw the mean line here, it is here like this. If all the variables, even if though there is an increase, they return to the mean, then we say that yes, your data returns to the mean, and then it is more likely to be stationary. But sometimes when we say a line has a trend, for instance, it keeps going up, 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 then we say it has a trend. Sometimes when you say a data has seasonality, then let's say maybe you check and you realize that it can go up and then it come back to its mean. And then it go up, it come back to its mean. So if you are into, let's say, ice cream business, and then you realize that sales increases mostly when it is around Christmas or maybe when it is around, let's say, Valentine period, then it falls back after the season, then you know that your data has issues with seasonality. So these are some of the explanations. Thank you. Now let's go into it. Now let's assume we've performed. I'm going to make assumptions because we have limited time to do the time series. Let's assume we've performed our stationarity test and then we realize our variables are stationary. So the first thing we have to do is to perform a simple regression. So that one, you go to statistics, you can go to time series, or you can go to linear models, and it's okay. So let's go to time series, okay. And from time series, you see you have other models you can perform here. But these are mostly what it's good to use them as your robust models. So we go to linear models and related, and we perform simple linear regression. Now, simple linear regression, we select our dependent variable. What are we trying to explain? Let's say we are trying to explain waste levels in our locality, as somebody asked. So our waste variable is probably, let's say, carbon emission. So let's use the CO2 emission. And then we want to explain it based on, let's say, trade levels. We want to explain it based on employment. We want to explain it based on even population in the urban centers. So you can go ahead and then you hit OK. But you can also go to the robust sections and then you choose to report standard robust standard errors. Mostly you use the robust standard errors when your data has more of heteroscedasticity problems. So let's start by going with the default, the OLS standard errors, and then we hit it. Now this is our dependent variable, which is carbon emission, and then we have all these things. So we've been able to explain the changes in carbon emission in our city based on trade, on employment, urban population. And I think you are okay with the explanation. So I'll pause here for a second and then you can come.
Can I go? Can I come?
Yes, please. Feel free to.
Yes, I just want to ask about data transformation. Because it's in different units. Some are in millions, I mean decimal points, some are in millions, some are like 0 point something, the indexes, and then some are in like very small. So when you transform, do you only transform only those big numbers, or do you transform the entire data set? Thank you.
Oh, okay. So it depends solely on what you are doing. You can decide to transform everything, or you can decide to transform the ones you think needs transformation, and then they make sense. Okay. So for instance, if all your variables are in percentages and one of them is in dollars, I think it's quite reasonable if you transform the one that is in monetary value to percentage. Okay, so that you know that all your data sets are in percentages. Sometimes the problem is if you don't keep them on a certain level of unit of measurement, when you do your analysis, you realize that some of them, they have a very big coefficient that you can't even see all the figures. It will come with E. And some of them, it will have 0.000. So you also have to be sure of those things. But for the transformation, it's solely dependent on you, which ones you want to transform and which ones you want to keep them at level.
Okay, thank you. Thank
Welcome.
you.
Now we can still go ahead. Now, after we've estimated our regression, we are making an assumption everything is stationary and all those things. So we can perform some diagnostics. And to perform the diagnostics, I think the very first one is you check if the residuals, which are being predicted, they are normally distributed. I hardly see people reporting these things of late. Like, I'm not sure if people still report them, but it's okay. So you start by just typing predict, and then you give a name you want to give. So the name, mostly people just call it the same thing, like a residual. And then you put a comma, and even if you put simple R, it will work. If you put residual, it will still work. And then you hit enter. So if you look here, you see we've predicted residuals has been added as a variable. Now we can decide to browse our residuals to have a fair idea of, sorry, I added S to the residue. We can decide to predict our residual variable to have a fair idea of how it looks like. So this is it. Some are positive, some are negative. So we need to know if they are normally distributed or not. So these are some of the things. So in order to know, you can just type the very basic command, which is the SK test, the silk test. So SK test. And then the name you gave it to your residual. So let's just go and pick the variable, and then you hit enter. Now this is our residuals test. And as you can see, this is the probability value. So we are safe. Okay. So the whole thing is like, we are not rejecting the fact that residuals are not normally distributed. But this is not it now. You should perform other tests. Sometimes you have to even perform the serial correlation. You have to perform multicollinearity. So instead of talking, let's just try some of them. You can just go back to your time series, and then you go to test for the Dickens-Fuller and all those things. But then when you go to the linear models, you can also find all the other models you want to perform. But since they are supposed to be performed after you perform the test, that is why we encourage you to perform all these tests. So we go in, and let's assume we want to perform our VIF. You just type VIF, and then you hit enter. Now, the VIF is to help you check, as we said, if there is multicollinearity in your variable, then the VIF will be very big. The mean VIF will be very big. When the mean VIF is above 10%, then you should be worried. However, I think you always find people argue about this. Some will say when it is 20%, some will say when it is 10%, some will even say when it is 7%. So the most important thing is that when your mean VIF is low, then you know that, yeah, your variables are not suffering from any form of multicollinearity. So after checking that, you can decide to go ahead, and you can also text for the heteroscedasticity, and then you hit enter. And as you can see here, it is also not significant, which means we are safe. So these are some of the things you need to perform to make sure that your model is okay. Now, the final test you should perform is what we call overspecification. Check if you've not omitted any important variable, or if you've not included some variables which are not supposed to be there. So that is what you do the STAT over test. Okay, so you see, the model says that the null hypothesis is that our model has no omitted variables. So here we realize that it is no omitted variables, but we have significant. So which means our model is suffering from some problems. We have some omitted variable issues. Now, when you find problems like this, you can go ahead and decide to add some variables to your data, or you can decide to just go ahead and perform other regression models. So I think I need to stop here. And mostly, I think the powers of the fitted value that we have much problem with is the carbon emission, which we are trying to explain. So there are other things that explains carbon emission more than just trade and, let's say, employment and urban population. Any question? Yes, please. After you transform your variables, it's better you go with the transform variables because that's the reason why you transform the variables. So that is okay. Okay, so, and there are other models you can perform. So let's quickly go into some of them. And we have 10 minutes to go into the other side of it if the variables are not stationary. So you realize that we also went into what we call the seemingly unrelated regression, and then we went into the quantile regression. So we can go to time series, and then we have the Winston regression model, which mostly you perform when you know your variable has autocorrelation or it is multicollinearity. This is Darwin-Watson is for multicollinearity, and this is also for autocorrelation. So you try to use some of these things to address some of the problems you have in your regression. So again, you select your dependent variable, which is carbon emission we are explaining, and then you select some of your independent variables. And once it is done, you can click on OK. And again, this is the results you have. So let's compare these results to the results we have here. Now you realize that log of trade is not significant in the normal regression, but employment and urban population are significant. But when you come to, sorry, my laptop is going slow. When you come here, log of trade is significant. And employment and urban population, yes, urban population is still significant, but employment, the coefficient is negative. This is where sometimes people based on to say that your problem suffers from some form of endogeneity. Because when you perform with one model and you use another model, you are supposed to have, even if there is going to be an improvement in the output, a significant one should still be significant. The direction, if it is positive, it should still be positive. If it is negative, it should still be negative. So when you perform your robust check with other models and you begin to have problems like this, it is advised to know that either your model is suffering from some problems. And mind you, we found out that our model had specification problems. We had omitted some important variables. So this is one of the things. We still realize that using our Winston regression, our data is still not suffering from any multicollinearity issues. Now, some people also prefer to check the whole multicollinearity thing first by conducting what we call the pairwise correlation, whereby you check the correlation in between your independent variables to be sure they are not highly correlated. One explanatory variable is not highly correlated with the other. So let's say there is no strong correlation between log of trade and log of employment. So to do that, you can go with the statistics, summaries and tables, summarize and discretes, and then you go to pairwise correlations, and then you choose your independent variables. Mind you, I'm not including the dependent variable because multicollinearity has to do with the independent variables or the explanatory variables. And then you perform it. You realize that for most of them, the correlation is not that significant. It is low, 0.4, 0.4. But when it comes to the correlation between urban population and employment, it is very high. So for this one, it will be better either you drop one of the variables or you begin to maybe find the difference, transform one of the variables. And that is why when we did our VIM, it wasn't like 1 or it wasn't 2, it was a bit higher. So you see the VIM for employment and urban population is revolving around 7. Any questions, please? I think we are behind time for the time series, so let's still go into it. Now, you can also go ahead and perform other kind of regression. So let's first just go to the linear. and then you did quantile regression the last time. Now, the quantile regression is when you try to check only part of your data. Now, remember we are explaining carbon emission. So we can first estimate for top 10% of carbon emission. And then we estimate for top 25%, top 50%. That's when we say we are doing a quantile regression. So for that, you select your dependent variable, which is carbon emission. And then you change the quantile here. Let's say 10. Oh, sorry. Oh, it's gone. So statistics. I realize I'm behind time, so I'm just speeding up a little. And where's my quantile regression? So you decide to check for just the first 10%, and here you can choose your independent variables. So the first 10%, you click on submit, and you see we have problem here. So the thing is telling us that we should use either a bandwidth or like a bootstrap quantile regression. When you begin to have some of these problems, it is okay. It is okay to have some of these problems when you are doing quantile regression. Now let's change here to 25. We'll come back to that and hit submit. You see, for 25% of the carbon emission, we can explain the top 25% carbon emission. And in doing that, we know that the only thing that causes carbon emission among the 25 highest carbon emission is urban population, and it is significant. We can go ahead and estimate for maybe 50%, which is half of the data, and we can also hit submit. And then we realize that, yeah, urban population is still a great factor when it comes to carbon emission. So the highest numbers are mostly probably going to be around the urban areas. You can go ahead and estimate for 75. And now for 75, you realize that as you begin to look at all the data sets you have, even employment level also begins to contribute to carbon emission. But still, trade has very less contribution, insignificant contribution. And this is how sometimes you do what we call the robust analysis with another model. So let me just close the quantile, and we go back to linear models. And we can go into, I think the last time you also did other models. Let's see if I remember. Is it multiple equations? Yeah, I remember you did multiple equations, which you did the seemingly unrelated regression. So for the seemingly unrelated regression, you go to statistics, and then you go to your linear models, and then you go to multiple equation models, and you go to seemingly unrelated. There's 3-stage least squares, whereby the model runs the regression around 3 times, including even the residuals and then the predicted values. So here too, the same thing. You just create what you want to do. You just click on create. You pick your dependent variable, which is carbon emission, and then you pick your independent variable, which is trade, employment, urban population. You hit OK, and then you can hit submit or something. And this is our seemingly unrelated regression again. So all these ones are going to be more of a robust model to the OLS, which is quite okay. So do you think we should take the break now, or we should wait for some second? Are we taking a break? Sunny, can you please shoot your question?
Yes, thank you, presenter. My question regarding this quantile regression is, can we use it for panel analysis? That's the first question. So if we are using it for panel and there is endogeneity, does it take care of endogeneity problems so that instead of using system GMM, can we use it in absence of
okay,
using
so if I was
because system GMM is very complicated.
Okay, so there is quantile regression for panel data, and the basic of them is what we call the XT-reg, which is panel quantile regression. So you can use that for, but it's something you have to install. It's a user-developed system at SSC. Now, you can quantile regression solve endogeneity. No, I don't think. And it wouldn't be able to solve endogeneity because endogeneity is mostly has to do with other variables you've not observed. And that is why when it comes to endogeneity, even GMM at level does not fix endogeneity. If you want GMM to fix endogeneity, you begin to add instrumental variables to your GMM. And so you see most people doing GMM with endogeneity issues. They'll either use the lag of the variable as the instrumental variable, or they will find another variable as the instrumental variable to fix the endogeneity problem. Okay.
So we can, so if there is endogeneity problem, and I want to use quantile regression, how can one go about it?
Yeah, you can still use the quantile regression. For instance, let's look at the quantile regression as I was explaining for fun. Okay, maybe we should limit this when we get to panel. Okay.
Okay. Okay.
Since your question is about panel, let's limit it. So I think we've not done all the time series one, but we have less like 3 minutes. So let's quickly go into it. Now, what you can also do is to perform what we call the ARCH or GARCH models. Now, the ARCH or GARCH models are very important when you are dealing with financial data, mostly like stock market, variables that are very, very volatile. It changes quickly. That is one of the benefits of using the ARCH and GARCH models. And you also have good control over heteroscedasticity and all those things. So let's see when we want to perform the ARCH and GARCH model. It's also very simple. The basic form of it is you choose your dependent variable, you choose your independent variable, and you are good to go. So this is the ARCH model, and you can go ahead, specify the lags. And remember, when you begin to add lag to a model, then we are looking at autoregression, the previous year explaining the current year. And that's why we call it autoregressive. Okay, now you hit OK, and this is your ARCH model. So when you look at the ARCH model, this is the previous year of carbon emission, explaining carbon emission. And we realize that we have a significant value. So if the past year carbon emission is very high, the likelihood that this year carbon emission will also be very high is there. And then you also have the normal regression output here being explained. So these are some of them. So let's go to statistics. We go to time series. We go to ARCH and GARCH, and then you can go and run your model. Okay, so please, let's take a quick 10 minutes break. As we said, we're going to take a break. When we come back, I'll try and go into the other part when your data is not stationary, because I think we have to do it, but I'll be a bit faster. So please have a short break and come back.
Okay.
We have 7 minutes to rest. Thank you so much.
Okay.
You say you cannot use that for
No, he said it doesn't take care of the endogeneity.
That's that process.
On its own.
Like
But because a friend of mine sent the paper to me on global value chains. So he used quantile regression for the analysis. And it's also fine.
content is just to show these are top. In sometimes some captions of this, especially this online news, they say 10 African countries with the highest GDP. Yes. So that is the use of content. It's just after doing your own analysis, then you reach content for support to support. But in just They use a baseline result.
We did factor probabilities and probabilities. This cover regression. Then in this VECM and involve probabilities. First one. Just for
Hello, everyone. Can we head back, please? So when you are back, you let me know, then we continue. Kindly
Please, it's
come
10
back.
minutes over.
Yes, please. It was 7 minutes, but we spent.
Hello, we are back.
Okay, thank you so much. It was just for me to grab water.
Yes, we are back.
Okay, thank you so much for coming back. Now, when we did the quantile regression here and we tried to estimate 10%, remember we were told we should use either a bootstrap or bandwidth quantile regression. So instead of you doing the normal quantile regression, then you have to choose the one to include bandwidth or bootstrap. And that one fixes some of these problems. So since you are back, let's just do that one. We go to statistics again. We go to our linear models and related, and then we find our quantile regression. Now, instead of choosing quantile regression, this time around, we will choose either a bootstrap quantile regression. Okay. Now, you see here, you specify the bootstrap, which is the number of replications you want to have. So it's just going to be what it is. just choose your dependent variable, independent variables, and then you can specify your quanta, and you can also specify your bootstrap. Sometimes it's just going to be you trying and then getting the result. So you see, it is worked here. But when we did it for 10%, just using the quanta regression, it didn't work. But here you see that the command is BS, which is the bootstrap, and then the regression. Okay. Now, let's assume you go into the analysis, you did your stationarity test. Sunny, do you mind muting your mic for
Different
us?
universities, all of them have their different.
There's somebody who is talking.
Hello, Sunny.
So far,
Do you mind muting your mic
Just
for
be
us?
asking you Q1 or Q2 or Q3.
Hello, Sunny, please mute your mic for us.
Oh, sorry.
Okay, thank you so much. Now, when you performed your stationarity test and then you realize your variables are not stationary, then you can decide to go ahead and perform your co-integration. Know that your variables converge in the long run. So you go to statistics and multivariate time series analysis. And then the first thing you have to do is to perform the co-integrating rank of a VECM. So you check if your variables are co-integrated in the long run. You choose your variables. Here, all the variables are used as dependent variable, because if you performed a VAR or Granger causality, one variable will be used to explain all the other variables. So just pick your variables. So carbon emission, trade, employment, urban population, and then you can hit OK. And this is it. Now, if you look at the results here, when the critical values are all small, on the surface, you realize that we don't have a star at any of the ranks. If the variables are co-integrated at a certain level, you always find a star at some point. So this is our Johansen test for co-integration. Any question, please?
Can you repeat this last one, please?
Please, yeah, of course, the same idea. Would you repeat it again?
Yeah, when you perform the vector regression, you are trying to see if in the long run, your variables kind of converge at a point.
Now we need from the starting from statistics.
Statistics. Okay, so you go to statistics. You go to statistics. You go to multivariate time series, and then you go to co-integrating rank of a VECM. Then you select your variables. You've chosen number of lags. You can decide to perform the lag selection, but mostly when you are dealing with time series, the lags can be 1, 2, 3, 4, depending on the number of periods your data spans. So I'm just going to leave it at 2, or maybe let me even leave it at 1, and then you hit OK. Now, when you look at it here, you know, when I come here, all my variables, this is it. Or this is all it is. When the critical value is bigger than the trace, then you know at least one of your variables co-integrates in the long run. Mostly the good thing is when you perform this test, if there's any co-integration and the rank at which it is, the software will put a star there. Please, do you get it now?
Yes.
Okay. Now we can say that our variable or our model converge at least once in the long run. So after finding co-integration in your model, you can go ahead and estimate a VECM, which is the error correction model. And if you found no co-integration, then you estimate the VAR. So mind you, the VAR, it's auto, vector auto, which means the previous year of a variable is also going to explain the change in the variable. So the previous year of carbon emission is also going to explain the emission of carbon in the current year. So we go to statistics. multivariate time series, and then we go to vector error correction model. Here we select our variables again. So we start with our dependent variable, and then we choose our independent variables. We are not going to go into the reporting and all those things. Now, when we look here, the maximum rank is 4. The maximum rank of co-integration is 4. So you can move this side to 4. To 3, it's 3, sorry. And then for the lag level, I just want to keep my lag at 1 because my data is very small. And I just go ahead and I click on it. Wow, so we have a lot of errors. Because beginning, we even found out our variable was stationary at level and all those things. It's not necessary to go into all these things. Now, this is carbon emission. This side is for carbon emission. This side is for trade. And this side is for employment. And this is the correction, the error correction. The error correction at 1 level, 2 level, 3 level. So all these things is looking at the long run, the error correcting, and then the co-integration. Because I included the error correction, the rank to be 3, that's why I have this. Now you come to the main model, and this side, it's not really necessary to explain because everything is an error. I'm just trying to give the idea of how to estimate your vector error correction model in case you realize that your variables are not stationary at level. Please, any questions so far?
Hello?
Yeah, hello.
Hello?
Yes, please.
I have a problem of this. Like, if you leave the error correction model at 1 and you run the model and you, like example, change this 3 to 1.
Yeah, I've changed it to 1. I'm just showing you.
Yeah. Okay. Now, where do you get your error correction model for the long run? Which one do you select? Is it the ECE for the dependent variable or for all the other variables?
Now, you know, mostly when you do the error correction like this is here, the co-integration, then the correction level.
Yes.
Yes. So we know that in the long run, there is a significant convergence. But here, we are looking at one variable being explained by the lag of the error correction.
Okay.
And when you come down here, it's also just explaining all these sides will become the basic normalization, which is the regression model. So for mostly when you do this, that's why you also go ahead and then you estimate your BS test, the BS test, which, hold on, when we finish this side, then we go into the BS test also.
Hello?
Hello?
Like which of the, like if you run your error correction model, which of the table will you report for the long run? Because I run this model, but I don't know. My problem is now, how do I report my output? Which part will be my short run and which part will be my long run?
Okay, so when you run the error correction model, as you've seen here, like I was showing you, this is the normalization. So this is going to be your long run.
Long run.
Yes. But unfortunately, because our variable does not have any problem with co-integration, we realize that variables were stationary. The results we are getting here does not make sense. We cannot use this because when we tested for our stationarity, we realized that variables were stationary at level.
Okay. So if you are reporting for the short run, are you going to report the above table, all the above table, you just take only the dependent variable part?
No, you know, if you look at most papers for error correction model, they are just focusing on the long run. So when you perform even this, and then you realize that the long run effect is not significant, it's still not necessary.
Yeah, I run it, but my long run, they are significant, but like the table above for the short run. So that's what I was confused. Should I report for the short run also, or I report for only the long run?
You can. You can. If you find out the short run and then the long run, it's like the ARDL model. Okay. When you find out that the short run and then the long run they are both significant, it is a plus for you.
Okay.
You get it. But even if you find that the long run is significant and then the short run is not significant, you are still good to go. It means that you are explaining the long run effect or the long run changes in your variable. But when you run it and then you realize that there's no long run effect, then there's no need at all. But for reporting sake, you can still go ahead and then if you are going to argue that in the short run, there is a positive significant or negative significant effect, but in the long run, there is no statistical significance. Please, do you get it?
Yes.
Yeah, so
for the short run, will I
report
report the whole table?
Yes, it's, you know, when it has to do with like the work maybe we are doing in school, you are supposed to write more words.
Yeah.
So you have to report every single thing. But if it has to do with, let's say, a paper whereby you are required to write just 5,000 words, then you can passively comment on it, and then you move to the main business of the day.
The long run.
Yes.
Okay. So from this long run table, where is the EC, the error correction term for the long run, the coefficient for the error correction term, the p-value for the error correction term? Because if I read papers, I normally see the coefficient for the error correction term and the p-value.
And then the p-value. Now, what we are estimating here, we are just estimating. Oh, so are you sure you saw a VECM or an ARDL? Because
no,
when you estimate the VECM, when you
Yes.
estimate the VECM as we have it here, we know that in the long run, we have a significant convergence.
Yes.
And then these are the coefficients, and these are their p-values.
Okay.
So in the long run, you know that, yes, log of trade is going to cause a negative significant effect on carbon emission. Please, do you get it?
Yes, I get it. But what I am confused about, like in most of the papers, you'll see, like for the error correction time, they'll say like in the long run, the error correction time will have like minus, or the error correction time normally have negative value, but I don't see the coefficient value for the error correction time.
Yeah, mostly you see the error correction model whereby we say that for the long run error correction to be significant, it has to be negative and it has to be around 1, and then it has to be significant. Yes.
Yeah.
So you see mostly that one under ARDL.
Okay.
That was why I was asking you that, are you sure the paper just ran the VECM and then left it? Or the paper goes ahead and then runs the ARDL?
Okay, I get your point now.
Okay.
So for the VC, you just look at the p-value for the error correction time.
Yes, and then you find out that if it is significant, then it means that in the long run, the errors are corrected.
Okay, thank you. Okay.
Okay, so let's say we've run our VECM, and then we found out that, yes, everything is in order. But then we only run the VECM when we know that we have co-integration at least in one of our models. Now, this whole regression here, it's invalid. One, because we didn't find any, we found out our variables are stationary at level. Two, we also found out that even the co-integration, I had to massage the ranks for it to be co-integrated. So whatever output you are getting here, you can't really make any argument with it. So we go and then we say that, okay, there's no co-integration in our model. So then we run a VAR. But once you want to run the VAR, it's still going to follow the same process. You go to your statistics, and then you go to your multivariate time series, and then you go to your vector autoregression model. The basic VAR is very simple to calculate. It takes less power, and it is simple to do compared to running the full vector autoregressive model. So let's start with the basic VAR. Here under the basic VAR also, you just select your variables. Okay, and you can decide to produce some graphs, which we call the impulse response function graphs and all those things. And you can specify the periods for the impulse response function. So once you specified everything, you just click OK. as I was trying to explain before we even started the VECM, the VAR model, it's using every variable as a dependent variable. And then it uses the lag of it to explain it. Now, this is our impulse response graph. I think I'll come back to the impulse response graph later. So here also, what you do is you pick every one of them as a dependent variable. You pick log of carbon emission as a dependent variable, and then lag 1 of carbon emission explains carbon emission today. 2 years ago, carbon emission also explains carbon emission today. Trade, current trade, or the previous year's trade explains carbon emission, and then 2 years trade, 2 years ago, trade volume also explains carbon emission. So this is how you explain it. Every variable in the model becomes a dependent variable, and then it also becomes an independent variable. And that is why you see carbon emission is a dependent variable being explained by all the other variables. Then trade also becomes a dependent variable and is being explained by all the other variables. So I'm going to leave it here if you have a question.
Hello?
Oh, I cannot download. Okay. Time variable not set. So, your time variable is year, capital year. So you need to set it. You are using small variable, small y. But if you look at your variable, it is all labeled capital. So it has to be T set capital year and then comma the year in small letters. And this will fix the problem. Okay, so let me find
thank you.
and go back. Okay, thank you. And then there was another question.
Hello?
Hello.
So if you run a basic var, like you have lag 4 or lag 3, the table will be very long. So should you report the whole table?
Yeah, you have to. And when it comes to the table reporting, it depends on how you are reporting it. You can decide to report them in columns. And when you're reporting your table also, mind you, you don't go reporting everything like the Z values, the P values, the confidence interval. You can only report the coefficients, and then you put the standard errors in parentheses beneath it. So it's just going to be like two columns for this one, and then 2 columns on the right-hand side for this one, 2 columns on the right-hand side for this one. So you'll be able to report everything. For the p-value, you don't report it, you just put star. For instance, if you put a standard error in parentheses, which is bracket, then you put the star 1, 2, 3 beside it. Then you put star 1 is like 10%, star 2 is 5%, star 3 is 1% significant levels.
Okay.
Okay, thank you. Now, you know how to do the ARDL. I think we spent most of the time on the time series, and I want to skip the ARDL because the ARDL is just ARDL. Once you have your ARDL, you can specify your variables. So in the short run, mostly you put the difference, so D, and you put your variables in brackets. Sorry, I'm going fast. Actually, I thought we could do this thing very slow. Okay, so something like this. Mind you, if I put D out here and I put all of them in brackets, Stata understands that I am taking the difference of every single variable. Do we get it? And then I can go ahead and estimate if I want the long run. I can go ahead and add the long run also. And then the long run, I just have to select my variables again. Yeah, so sometimes you just run your ARDL like this, and you can put your EC there. I think it's not gonna work because there's a factor variable selected. I have added a variable which is having like none. Okay. Oh, I'm still having a factor variable. I'm not sure. So let me just switch into the, and then I'll just browse the data and come back to this. So is there any question on the time series for the time being?
Hello? Hello?
Okay, so hello.
Hello? So for
Hello.
the ARDL, should you run it on level or at difference?
No, you can run the ARDL if there is level or phase difference.
Yes, okay.
Yeah, whatever we are doing here, it's not gonna work because we realize that our variables are all stationary, so which is okay. You can go ahead and run your ARDL.
I
The
normally
ARDL, the
run,
point is that there shouldn't be.
I normally run the ARDL on level, so I thought it should not be run on level at different. So I normally have insignificant value. So when I saw you are running it on different, that's why I'm asking whether we should run it on different or at the level value.
Yes, the ARDL is okay to run it on difference, and that is if your variable is either at level or as phase difference or a combination of both. You are okay to run the ARDL. But it becomes tricky when you are running it on the second difference levels.
Okay, thank you.
So most of the ARDL commands you will see, you will always find out that in the short run, we will take the difference. And then in the long run, either we will use the lag or we will keep it at level. Is it okay?
Yes, it's clear.
Okay, thank you. Okay, so how does the lag time affect the results? Now, the lag is more like a previous year. Lag is a time. So let's say I am trying to explain, expenditure, okay? Or if I know like your field, I would have made a much clearer example. Let's say I'm trying to explain like GDP. So I know that if last year the country did so well, then the probability that this year they will do well is high because some of the factors of production, the economies of scale from the previous year will affect the current year. Is that okay? So that's why we bring in the previous year. It's not going to change the level results, but then it also gives you the opportunity to explain the previous year and its effect on the current year. So for instance, if I did very well in my studies last year, the assumption is that the probability that I will do well this year is very high because I did well last year. I have known how to study. I have equipped myself very well, or maybe I'll be motivated to even study well and then pass this year's also. So that's when we bring in the lag result. Is it okay, please?
Yes, it's okay.
So increase and decrease the lag time, it does affect the results. Yes, it will, because now you're including in more parameters. You are bringing in more parameters. You know, when you have a regression with just one variable, let's say, let me close this. Well, we're not gonna finish today. If we have regression with just these two variables, you realize that the coefficient is 0.082. Now, when I go ahead and then I introduce a third variable, you see that the coefficient has reduced here. Even employment is no longer significant. So when you are bringing in the previous year and all those things, just be careful because they still have effect. For instance, let's look at this result. If I decide to introduce the previous lag of employment, you see I'm getting way different results, different coefficients, different p-values. This is 0.38, but before it was 0.43. So you see it is making some changes in the model. If I go ahead and then I introduce a second lag, I am still going to get very different results. So these are some of the things. Okay, so thank you so much. And I think we spent so much. Now, the determining of the maximum lags, we can even use the VECM rank to determine it, but it's also sometimes you can just look at the data set you are working with. If the period it's very short, less than 10 years, 20 years, and it's a time series data, it is better you go with one lag or maximum of 2 lags. But if you want to go through the process, you can decide to go ahead and then use the lag selection model. So the lag selection model, we go to statistics, multivariate, and then we have what we call the test. So let's go to time series first, and then from time series you can go to post estimation, the tag for unit roots and multivariate. Can you hold them for me? So we have what we call the diagnostics, and from the diagnostics we have the lag selection, post estimation, and pre-estimation. So you can select your lag selection from here. So if it is pre-estimation, before you conduct your model, you can just come here and select your model. So it starts with the log of carbon emission, which is log of carbon emission. And this was where we had our model up to. And you see, you already tell STATA an assumed lag level. That is why I was saying that sometimes you don't need to go through this. And then you just click on OK, and it will estimate and show you the lag level to use. See, STATA is giving us the 4 lags. But then if you have very small data, why do you want to use 4 lags? This one is saying our data is from 1995 to 2020. That is quite a good data then. Let me check. Oh, 1991 to 2020. Yeah, that's quite a good data. Then it is okay if you are using about 4 lags. Please, is it okay? Oh, okay, thank you. So, Kanju, is it okay for the lag selection? Okay, so we go ahead. Okay, thank you so much. We go ahead. I don't remember the last time I did lag selection though. Can we switch to panel data if you are all in agreement? Okay, so let me clear my screen. Now we're going into panel data, and I would suggest you take 2 minutes break, just grab a cup of water, and then just cool the time series off. The data we are using is what we were given from the lectures. Data set 1, data set 2. I decided to use it, the same data set. So okay, so I think we are good to go. Now, last week, when I was doing the recap for the panel data, I decided to show you a graphical approach to go through all this. And then I realized, even though I thought a simple one was enough, people still showed interest. So I decided to go deeper. So now I'm not going to use this particular one, which is a bit easier. I'm going to go into one which is a bit much complex. So this is what we have. You have a panel data. Your data is randomly sampled. Then you know that your data can qualify for a regression analysis. Some questions you have to ask yourself is the period and then the number of entities. Panel data deals with either entities, countries, like different people or different countries' data put together. So when you realize that your number of entities, which is normally called the N, or observations, if you realize that the number of people you have data on, countries you have data on, is bigger than the time period, then you can decide to be thinking about GMM. It's easy for people to use GMM, and because people feel like GMM is a robust model, it controls for endogeneity and all those things, people just go to GMM straightforward. But if your time period is higher than your number of entities, then even using GMM makes your results wrong. Now, if you realize that the number of years is bigger than the N, then you can decide to go into the normal regression we do. You test for co-integration, and then you do a VAR or a VECM analysis. So when the T is bigger, but the N is smaller. And sometimes we are saying like 25 years of data is an average good or enough data. So any first generational panel regression. But sometimes it's difficult to even have data set for 25 years. Talk less of having data on 25 entities. Now, when you realize that both your time period is small and the number of observations are also small, then you have to look into time invariant analysis, which we call the OLS, the fixed effect, and then the random effect. So is it okay on the right-hand side? Okay, I assume it's okay here. Now we come to the left-hand side. The left-hand side is when you begin to go deeper, and then you begin to look at cross-sectional dependency. You have very big data set, more time period, more entities. So let's say I'm conducting a study on Africa. Even though there are about 54 countries or 55, depending on wherever you see it, you know that some countries are dependent on each other. So there is a likelihood of cross-sectional dependency. For instance, we can just say that, oh, when the economy of, let's say, Togo is good, then the other Francophone countries in West Africa are most likely to also have a good economy that particular year. So there is some form of dependency on them. And then you need to go into estimating for cross-sectional dependency, and then you look at your stationarity and all those things. With this said, can we go into an analysis?
Yes.
Okay.
Any question? Any question, please?
We can go to the analysis.
Okay, let's go to the analysis part. So we begin our analysis by importing a panel data. So we go to import time series, and then again, we could have decided to walk through the data in Excel, but I'm not going to because you know how it goes. So, and you choose the sheet you want to work with. This time around, we have data in only one sheet. So that's all we have. Import first rows as variables. I prefer to work with lowercase, and then I hit OK. So this is my variable. Now you realize I have ID and I have country, and then I have year. Now, the country is the same as the ID, but then the ID is like the numerical representation of each country. So let me browse ID and country. And as you can see, 1 is being assigned to China, 2 to India, 3 to Indonesia, 4 to Malaysia, and up to 9. So we have very small data set. Very small data set. So we have lower N, we have lower T. T is, I don't think T is even more than 25. So let me add T to it, and then we estimate from 1991 to 2020. Okay, that's also a good amount of data. So from 2000 to 2020 alone is 20 years. And then from 1990 to 2010 years. So we have about 29 years of data. So if we have about 29 years of data from here, we know that we have a bigger T and a lesser N. So we can just go ahead and begin to do a co-integration test to find out if we can run some of these models. But since this is for recap purposes, I'm going to go through everything again. Now, once you have your data, the first thing is you perform your stationarity test, which I know you all know how to do it. So we go to statistics, and the first thing we have to do is to tell STATA that we are dealing with a panel data. So we go to longitudinal panel data, and then we go to setup and utilities, and then we declare our data set to be panel data. So we pick the ID, and then we tell STATA that yes, we have a time variable, and then our time variable is the year. Our data is a yearly data. We hit OK. Now we told STATA we are dealing with a panel data from 1991 to 2020. We can go ahead and run the stationarity test again. So statistics, we go to longitudinal, and then we can go to unit root test. From unit root test, you pick one variable at a time, and then you perform the unit root test. No observation for, oh, I picked year. Okay, so log of truth. Okay, voila. So as you see here, we say that the null hypothesis is that our panel contains unit roots. And then the alternative is that they are stationary. So since our p-value is bigger than 5%, we then conclude our panel is stationary. You can go ahead and run for the other ones as well. Okay, so here we have a problem. And then we can decide to see if the data can be stationary at first difference. So just take D dot as in first difference. And we still realize that we have a problem. So we can take the second difference. And we still have a problem. So this means that this particular variable needs transformation. We could transform this variable as it is, or we can drop this whole variable altogether because we have a problem with the variable. So since we have a problem with this variable, let's just go ahead and look at the other ones. Employment. Okay. Yeah, so here we go. We have a lot of problems with our data. Okay, so these are some of the things. And then you know that, so you begin to think about how to transform your data again and all those things. But that is not going to help in this case. So since we know that our variables are not even stationary at level, then we can decide to be thinking about going to the vector co-integration test and all those things. Any question on this one? Please, any question on this one? Okay, so we continue. Okay, guys. If your variables are stationary at level, you can just go straight into the normal regression. It follows the time series analysis. If they are stationary, then it's a good thing. You begin to conduct your analysis. Okay, so let's go. Now, the first thing we want to do is, assuming everything is perfect, let's perform a fixed effect analysis. Then we perform a random effect analysis. Then we choose between fixed effect and random effect, which one we should work with. So we start by going to statistics, then we go to longitudinal panel data, and from the longitudinal panel data, we can go to linear models, and then we run linear regression. From the linear regression, We can decide to run fixed effects, between effects, and all those things you want to do, the average mean regression, and then the likelihood analysis. But the basic of it is to first begin with fixed effect, because we argue that if your data, panel data, you have more years over a period of time, there's a likelihood of a time invariant kind of effect. So pick your dependent variable, which is carbon emission, and then you pick your independent variable, which is log of trade, employment, urban population, for example. Now you can go ahead and hit OK. And this is the results you have. You have a very good R-square. You have a chi-square being significant. And then you begin to know that probably fixed effect is the right model to use. But we can't just jubilate yet. No, this is random effect. Sorry, I didn't change it. Let's go back and run the random effect. Praise, can you not draw on the screen for us? So longitudinal panel, and then we just go to linear models. The first thing is we are running the fixed effect model. So you change here to fixed effects. Please, is the clarification okay on this?
Yes, it's fine.
Yes.
Okay, thank you. And then we hit OK. So we have fixed effect again. And as you can see, we have a very nice R-square. We have a significant model. And then we know that the time invariance is also significant. And about 95% of the changes in our model is being explained. That is perfectly okay. But we need to compare it with random effect. So you first save this result. Then you type estimate, store, and you call it whatever you want. So we just call it FU mostly for short. The next thing you do is you run the random regression. So statistics, longitudinal, and then linear models. You go to linear regression. And this time around, you choose the random effect, and then you hit OK. Again, you also have a very good result. So you save it. Estimate, store, random, RE for short. Now, once you have this, you can go ahead and run the Hostman test. Now, the point is, we are trying to say that both random and fixed effect, they are all good models to use. So both random and fixed effect, there is no significant difference between the results. And then the other thing is saying that, oh no, we should supposed to use a random effect. So the point is, if our p-value is significant for the first one, then we are going to use our fixed effect. If not, we are going to use our random effect. So we go ahead, we can go to statistics, and we can go to post-estimation. But before, let me check. We can go to our post-estimation, and then we can conduct some of our post-estimation tests here. So specification diagnostics, and we choose Hostman specification test, launch. And the first thing is we are checking for the consistency of our estimation with fixed effect. You can decide to leave here empty, you still get the same results. Or if you like, you put the random here. That is why mostly when we type the model, we type Hostman, F-E-R-E. So let me begin by cleaning this side and show you. And then you hit this. Now, as you can see, this is the fixed effect. The coefficient for trade is 0.22. The coefficient for random effect is 0.22. So you realize that there's no significant difference between them. For employment, there's no significant difference. For urban population, there's no significant difference, which means that we can go ahead with the random model. But as I was explaining, even if we decide to put the RE here, so that we have Hostman F-E-R-E, now we have just Hostman F-E, and we click OK, we are still going to get the same results. Now we know that we are supposed to go with the random effect. Please, any question on this?
Yes.
Okay.
So I was looking at when you estimated the on the results, I was looking at the the R squared and also the raw. How do you make the difference in interpretation?
Okay, so hardly will you even see someone explaining the ROH because it has to do with the variance in the model explanation. But the general R square explains the model explaining the dependent variable. So here we are saying that 95% of the variation of the variance are due to time invariant effect. But the R square here is saying that 78% of the variability in carbon emission is explained by these three variables. Please, do you get it?
Yes, I do. So the
In
raw
case
is
of
time
unbalanced,
variation.
yeah, no. The
What you
raw
say?
is about the variance. The
So
ROH is about the variance. And then the R
the
square
variance.
is about the model. Yes.
Okay, thank you.
Okay,
Hello,
welcome.
Prof, can you come again? You said the raw?
The raw has to do with the variance. The ROH has to do with the variance. And that is why no one even, hardly would you see someone explain the sigma U and the sigma E and then the variance. Because this has to do with just the variance in our model. But when you look at the R square is trying to explain the dependent variable, how the independent variables explains the dependent variable. Do you get it? You know how you calculate your standard deviation and then your variance?
Yes.
Yes.
Yes. So the sigma U, the sigma E, and the ROH, it all has to do with the stability of your model. It all has to do with the stability of your model. But then the R square has to do with the explanatory power of your model.
Okay, thank you.
Okay. Now, in case of unbalanced panel, how do you check for stationarity? Just go ahead and do it. Yes, you can check for the stationarity in unbalanced data as well. It's the same thing. The good thing is if you have a balanced panel, it is good. Sometimes some of the stationarity variables methods we use does not allow for you to use unbalanced panel. So when you go, you choose, when we're dealing with the stationarity, the unit root test, for instance, when you come and then you choose, I think mostly for unbalanced data, the Fisher unit root test is what you'll be using because some of them do not allow you, some of the methods do not allow you to use them on unbalanced data. But then it is the same process. You just have to choose the method you are using here. Is it okay? Okay, I think Abdul is just typing. Okay, yes, so we go ahead. Okay, so this is some of it. Now we know that we are supposed to use random effect. We know that we are supposed to use random effects for our analysis. So since we are supposed to use random effect, we then also have to check if a pooled regression is better than a random regression. So now we found out that there is no there is no country-specific effect. So we are running a random regression. But then there are instances whereby even there is no randomness in the model at all. So we need to pull the regression together and then we run it. Please, any question?
Hello?
Hello, we are listening, sorry.
You said you have to check between random and pool effect. Which one to select? How do you do that one?
Oh, yeah, we are going to do, but I was asking if the explanation is okay. Now,
Yeah,
the STATA is saying that country fixed effect is not of importance. So we have to run random regression. But we also want to check if there is randomness even in our model, or we should just put them together. So in doing that, that's when you use the XT test for the Lagrangian multiplier test. But we can also do it by coming to statistics, and then we go to our post-estimation. as we did for the Haussmann, and then we can choose to use the Baruch and Kagan Lagrangian multiplier test for randomness. Mind you, this time around, we are testing for randomness. So we are saying that there is randomness in our model. That is what we are checking. So when the p-value is less than 5%, then we can go ahead with random regression. If it is higher, we go with a pooled regression. Is this okay? Okay. So I'm going to close it. And now this is it. We run our Lagrangian multiplier, and then we realize that, yes, there is a very high variance, and then our p-value is 0.00, which means there is randomness in our model. And here, we can then decide that instead of running a pooled regression by just typing REG and then our variables, we have to use XT REG. Please, any question on this? In case of no randomness, you just run a simple linear regression by just using REG, your dependent variable, independent variables, and then you run your OK, and then you can go ahead and do the normal test we did for the OLS regression. You do the OV test, you predict the residuals as we work through during the first half. Please, is it okay?
Yes, it's clear.
Okay. Yeah, so now since we are dealing with panel data, they are different countries over a period of time. Sometimes it is okay to go into what we call the cross-sectional dependency. So to do the cross-sectional dependency, there is the first generation and then the second generation. The first generation is a bit easier to do, but then the second generation is more robust. So let's say we want to do a first generation cross-sectional dependency test. That is when we have one like the STCD, and we can go ahead and select our variables and then hit OK. And as you can see, we found out that when it comes to carbon emission, there is cross-sectional dependency among the countries. When it comes to log of trade, there is cross-sectional dependency. So no one country is dependent on itself. They all affect each other. And if you look at the data, we are dealing with a particular Asian bloc, China, India, and those things. So it is okay to have some dependency in it. So intuitively, it is okay. Another thing you can also do is to run the second generational cross-sectional dependency test by Pezaran, which is the STSCD. Okay, let me try, and then comma Pezaran, and then you tell Pezaran that you are using the absolute values and you hit enter. Okay, so I think my command is wrong. Let me quickly check if I can get the command right. STCSD. Oh, last estimate.xt reg. Okay, so because we ran a pooled regression, we have to run back our random regression. So let's run it. And then we run our Pezaran. Okay. Please, is it clear, the confusion? Is it okay? Or do I have to go over it?
Yes, please.
I go over it. So we ran our regression model, and then we realized that there's randomness in our data. So we also want to test if there is cross-sectional dependency in our data. The countries depend on each other. So to do that, you can either run a first generational cross-sectional dependency test, which you use this command, which is xt cross-sectional dependency, and then your model, the dependent variable, and then the independent variable. Now you realize that all of them have some form of cross-sectional dependency. The p-values are significant. Alternatively, you can perform what we called the second generation cross-sectional dependency test, where you use the Pezaran cross-sectional dependency test. So XT, CSD, and then the Pezaran, then the absolute value. So we found out that there is a significant cross-sectional dependency, and yeah, we can say that the entities we are working with are dependent on each other. So this time around, even if you performed your random regression, it will be okay to perform a cross-sectional dependency as another model. You can decide to use cross-sectional dependency as a robust model, which isn't that very good, but it's better than just running only random regression. Please, is it well understood?
Yes, it's okay now.
Okay, so why don't we take a 5-minute break so we kind of discard this whole test off, and then we come and continue. So let's have a 5-minute break. We come at 57. Okay, what value can we say there is no cross-sectional dependency? When the p-values are not significant, and then there are tons of other models to run with panel regression. So panel regression has lots of models. So after you've run the first generational, second generational, if you don't find cross-sectional dependency, it's okay. You can go with your regression models, and that is okay. Alternatively, you can just check and pick some of the models here. So let's just take a break and come back at 57.
One focuses on integration. We focus on social regression, such as correlate and explanation of expression output. We also look at the right it's about panel data model which structure is the transform. Four, we focus on survey data analysis and treatment with Dr. Toba. Looking at primary data analysis and business. Five, focuses on conceptual framework development and relational graphs. Talking about survey design and conceptual evaluation chart. Then we run out all the programs. Online. Then, what is your goal? Well, answer is nothing or online. Go from 0 to 0 without 5. One focuses on integration. We focus on social regression, such as correlate and explanation of expression. We also look into the right one. It's about panel data model which Four, we focus on survey data analysis and treatment with Dr. Toba. Looking at primary data analysis and treatment. Five, focuses on conceptual framework development and relational graphs. Talking about design and conceptual evaluation. Then we run out all the programs. Thank you. All right. So
Okay, hello everyone. So I think we can come back and then we quickly go through it. Wow, like I'm not sure if we can finish, but we'll do what we can. So let's come. So can we continue? Hello everyone.
Yes, we
Yes.
can
We can continue.
Okay, so let's continue. Thank you so much.
Yes, yes.
Okay, so let's assume when we perform it's an assumption, so which means I cannot guarantee the quality of the results. Let's assume when we perform the Haussmann test, we're supposed to go with fixed effect. So if you're supposed to go with fixed effect, what should be your worry is the homoscedasticity of your data, of your model. So let's first run your fixed effect. So this is our fixed effect. We have very good results, but then we don't know what is going to happen. So we can go ahead and also text for that. And the simple way, instead of going through the statistics, let's try this. And then we realize that it is significant. We have a problem. So how do we fix it? I think a very quick around people use to fix this is by imposing the robust standard errors. Because if now you are using a robust standard errors, it kind of adjusts some of the estimation, the coefficients, and sometimes it can even translate into the significance levels. Because this time around, the standard errors are being handled very well, and you know that your data is your output is quite better. So let's try and impose a robust standard error on it and see. So we say D3 robust. I'm not using the STATA interface because I assume you've done it and it's okay for you. Now, when you use the robust standard error, you realize that our coefficients are here, our p-values are here. Let's cross-check with this. Without a robust standard error, we realize that all our variables were significant with a p-value of 0.000. But with a robust standard error, we even realize that the employment variable is no longer significant. So we are controlling for some of the noises. And that is why you are supposed to do this to be sure if you need to even impose a robust standard error on your model. Now, we found out that there is heteroscedasticity, and we also found out that our data suffers from cross-sectional. In this case, I think it would be a bit better if you run a cross-sectional dependency regression, and then you use another model which can control for cross-sectional dependency and heteroscedasticity as your robust model. You understand when we're going through what it means by a robust regression, you either change your variables at some point, include some variables, or maybe use a better model to check it. So since we found out that our variables or our model suffers from cross-sectional dependency, we can decide to run a cross-sectional dependency regression, which is almost the same. It's just STSCC, and then you pick your variables. So our dependent variable, our explanatory variables, and this time around, we are using fixed effect and robust standard error. So we put fixed effect, and then the VC is as robust, and we hit and oh, not allowed. So let me just see. Let me see. Oh, robust not allowed. Kindly hold on. If we put our fixed effect, we are going to get a result. But Hold on for me. Let me see. Oh, okay. So we don't need it. We actually don't need it for here. But that's strange. Okay. So we just perform like a robust a fixed effect or random effect using the cross-sectional dependency model. So we already found out that there's a cross-sectional dependency in our model. So we perform a cross-sectional dependency regression instead of the normal fixed effect regression. Please, is this okay? Is the confusion clear? Hello? Hello?
Hello.
Yes. Is the confusion
So,
cleared or there's a question?
you said if you realize that there is a heteroscedasticity in your data, you either run robust standard error model or you run cross-sectional dependency model.
Yes. Yes. But the cross-sectional dependency, you also have to test, like we tested using either the first generation or the second generation. Either
Okay,
using
like where we tested in when the data was not set, did the same, we have to follow the same test before you use cross-sectional dependence.
Yes, please. You have to argue that you did this test and then you found out that your entities are cross-sectionally dependent on each other. Then there is a reason for you to conduct the cross-sectional dependency model.
Yes. Hello?
Yeah, hello.
Yes. As we now, I think we have two problems, heteroscedasticity and the problem of cross-sectional dependence. Then how we have to proceed?
Yeah, so when we use the robust standard errors to fix the heteroscedasticity in the XT regress, we are done with that. So we can then go ahead and use a more advanced model, which is the STGLS or the PCSE model. I'll go through that with you to correct for cross-sectional dependency and the some of these things like autocorrelation and all those things.
Yeah,
But what I'm trying to say is,
yeah, I'm saying that when you introduce the standard robustness, actually it has given fake results because it has even the probabilities were good, but after introduction of standard robustness, the probabilities are no longer significant. So I think it was not after getting that. I think what can we do, because actually the model is becoming very bad or somehow very wrong because we introduced the robust standard error. So, or how to proceed?
Okay, thank you. Okay, so when you introduce the robust standard errors, it doesn't mean the model is becoming bad, even though you are getting a result that's not what you were looking for. It means that this time around, you are even doing the right thing. Because your model has a problem, and then you are fixing it. When you don't fix it, you are going to get a spurious analysis or like output. So you need to fix it. That's why we introduced the robust standard errors. So if you introduce the robust standard errors and then you realize that your model is no longer significant, that is better than you not introducing the robust standard error, even when you know your model suffers from heteroscedasticity and then goes ahead to report a spurious output because they seem better. Do you get it?
Yes, thank you. Thank you very much.
So after you fixed it, if you fixed it and then when we fixed it, you realize that we had some average good model, trade is significant, urban population is significant. There are instances when you introduce a robust standard error, you might even have everything not being significant, or even the model not even executing or telling you multicollinearity and other things. But then it is still better. Then you know your model has a problem. So you can then look for another model which is good at it. Now, what I was trying to say is, even though our model was for us to use, our test showed that we should use random regression. We are testing with fixed effect also. So it is also good for us to test if there is cross-sectional dependency. We tested and we found out that there is cross-sectional dependency. So if you still go ahead and run the fixed effect regression, you can run the cross-sectional dependency as some form of a robust check, because that model fixes the cross-sectional dependency problem in your basic fixed effect model. You can also go ahead and use other models to do that. Sometimes people will go ahead and begin to look at endogeneity and other things, but that is not what we are looking at now. We may get there. So if it is okay, I can proceed. Is it okay?
Yes, it's okay. It's okay.
Thank you. So now we found out that this is the point. And when I was showing you the PPT, there was a model I was just speaking of. We have the XTGLS and then we have the PCSE. So you found out that all of them can do very good when there is some form of cross-sectional dependence. But it's like using GMM. When you find that your N, which is your number of entities, is greater than the time, okay, then you are supposed to go ahead and use what we called, even in our case, we found out that our T is greater than our N. So the best model to use is the XTGLS. But in case that our N is rather bigger than our T, then we could have gone ahead and used our PCSE. And I just put the syntaxes also here for you. So let's go ahead and try it. To do that, we go to statistics and we go to longitudinal. And from here, we just go to our contemporaneous correlation and we go with GLS because our T is far bigger than our N. So when we come here, we can fix cross-sectional dependency. We can also fix heteroscedasticity in our model. So let's pick our dependent variable, which is carbon emission, and then we go ahead and choose our independent variables. Now, if we had other issues such as multicollinearity and all those things, we could have fixed them here. So I'm just going to keep it at the basic level, and then I just click on OK. And you see, even with the more advanced model controlling for heteroscedasticity, compared to we just imposing a robust standard error, we still found out that employment is not significant. But then trade is significant and urban population is significant. So we can then use this one, which is cross-sectional time, heteroscedasticity, and autocorrelation corrected model. We can use this one as a robust model. Please, is it okay?
Yes, continue.
Okay.
It's okay.
Thank you. Okay, so in case we found out that our N was very big compared to our T, then we could have done the same thing, but this time not using XTGLS, but then we just go and use our PCSE. So contemporaneous correlation, regression with panel corrected, standard error. So we choose our dependent variable carbon emission and then our independent variables. And here we say there is no autocorrelation, but then we have autocorrelation in our model. We can also go ahead and choose if there is the type of autocorrelation we want to use method to compute, whether Darwin-Watson or the normal OLS. And here we also choose the error we have. So we had panel level heteroscedasticity, and also we had cross-sectional dependency. So this is the best to choose. In case we only found heteroscedasticity, but we didn't find any cross-sectional dependency, we could have used this. Or if we found cross-sectional dependency, but no heteroscedasticity, we could have used this. So you just pick this and hit enter. And once again, this is our result. We still realize that employment is not significant. So this is how you use one model as a robust check for another model. I am trying to send this one home because sometimes I think some people will be like, did you perform robust check? Did you perform robust check? Either you change some of your variables or you change your models. Please, any question up to this level? Hello.
Yes. I have a question. Is this final one, this correlated the panel corrected model? Is it incorporating the two problems, heterogeneity and the cross-sectional dependence? The two.
Yes, please. Yes, it is correcting both because we chose both.
They both two.
Yeah, we chose that our model has heteroscedasticity problem and then there's cross-sectional dependency. So which means we are correcting both in the model.
Yes, thank you very much.
Okay. Now there are other things you can do. You can perform okay, there's a question. We have to take a quick break and move to the survey data. Okay, let me say good luck. Why we should present analysis of both models by presenting this and that. Yeah, that's what I'm saying, that in case you want to use the cross-sectional dependency as a robust model, then you need to report both. But in case you want to just discard the fixed effect model and then use cross-sectional dependency and maybe a GLS or a PCSE, then there will not be any need to report the fixed effect model. But then I think it's also up to you. You can decide to comment on both. Just have a table of three columns and then you'll be good to go. So these are maybe preferential kind of thing. Okay. So with this said, I know you know how to perform the ARDL for panel data, which is the same. You just add PMG for pool mean regression or difference fixed effect model. So I don't think we should go into it. What do you think?
Actually, I think we still have the problem of androgeneity. We didn't check the androgeneity in the model, I think.
We didn't check for endogeneity. I explained the problem of endogeneity to you. The problem of endogeneity is when you have other unobserved variables, okay? And then you cannot observe them, so you try to either use a proxy to check for that. That is one of the main endogeneity problems. For instance, it becomes like endogeneity, mostly you are dealing with an instrumental variable kind of thing. Let's assume we want to perform a GMM model. So let's go to longitudinal, and then we go to dynamic panel, and we are going to perform the basic, not the system and all those things, the other GMM models. So let's say we are performing this, and we decide to perform the system GMM model, not the likelihood GMM model or IVGMM. So we choose our independent variable. We choose our independent variable. Okay. Now this is the part where you have endogeneity, endogenous variables. So you can come and select your endogenous variables. So let's say my endogenous variable here is, let's say, employment. Okay. And then I want to control it by adding even a lag variable. These are some of the ways, some of the basic ways you see people correcting for endogeneity in their model. They will quickly go to GMM, but the whole issue of endogeneity is very complex. Sometimes even finding the right variable as your endogenous variable, or like your IV to your endogenous variable, is a big thing. Please, is it clear on this?
Okay. Let's see what comes out.
Let's see what comes out. Okay, so this is it. Because we chose to use the lag of our endogenous variable as our employment, that is why we have it here. That's why we have it here. So we are saying that our lag employment variable is an endogenous variable, and then the lag of it, we added a lag structure. So when you run something like this, mostly people will argue GMM controls for endogeneity and just end it there. But it goes beyond just, we know GMM can control for endogeneity. But even you identifying the right IV variable, it's the thing. And this is one-way endogeneity or GMM model. You can go ahead and perform the two-way, like the way we have two-step regression, the seemingly unrelated, two-stage least square, and all those things. Two-stage least square, IV, they all addresses endogeneity, and people also use GMM, which I'm still not very sure, but I know people uses it, so I can't comment on it. So we come here, and we can also decide to compute the two-step estimator instead of one. And you see, the two-step is not working because we have multicollinearity in our model. So which means we could have been stuck with this. And then we argue that we've introduced an IV and all those things. So let's go into this one also. Dynamic panel data, arena bound. Here, you see we have the option to include additional instrumental variables. So you know from here, you are basically controlling for endogeneity in your model. So we pick our dependent variable, which is carbon emission, and then we pick our independent variable. Okay. Now, when it comes to additional instrumental variables, the easiest argument you see is that you use the lag of the various variables as the instrumental variables. So you just put the variable, you put lag, you put your second variable, and you put your second variable, urban population. Let's assume this is it. And then you can decide to estimate, and you see, now, this time around, we have number of instruments involved, and this is our output. So then you are going to argue that you have used the lag values of all the variables as instrumental variables to fix a possible endogeneity in your model. But I'm not sure if this is very sound to do instead of going through the traditional way of finding an IV. Also, another thing you have to know is that before you use GMM, know that your number of entities should be greater than your time period. That is a very basic assumption, which mostly you see it being skipped. Any question?
It's okay.
Okay, thank you so much. So I would want us to take a quick 5 minutes break so we can go into the survey data, because I think Dr. Robert gave you how to use the dynamic OLS command, and he also gave you the ARDL for panel data, which is the pooled mean regression, whether you estimate here to be a pooled mean regression or a dynamic fixed effect or mean group. So you only change these ones, whether you want MG, PNG, or DFE. So I think with this, I am safe if I skip it. You made it very clear in there. Hello?
Is this PDF shared in the group? Because I don't have this PDF.
Which one? The PDF, we sent it in the group. I sent it in the group, so.
Okay.
Yes.
Yeah, so please, I think
I have the problem. How can I get your, I want to get your WeChat. I want to talk to you personally.
You know, for me, I am a student following the doctors. So that's why you are supposed to contact the doctors if it's anything technical, because my knowledge is very limited. So that is why.
No, it is not
Thank
like
you.
that.
Thank you for understanding. And let's take a short break. Let's have a short break and come back.
Maybe you don't want, right? You don't want, right?
Oh,
All
no,
right,
no,
all
no.
right.
My knowledge is very short. Like, you know, I'm still learning. So
That is not what I want to ask you. It is another issue.
Oh, okay. Okay. Yeah, like I
Yes.
said, if it's anything technical, you contact doctor. If it is any other thing, then yeah, we can talk. But for the technicalities, I'm leaving it to
But
the
I
head of
don't
this.
know. I don't know. Are you Hwame? I don't know your name on which.
Oh, okay. So I will find you. Let's see.
Okay.
Fine. Yes. Okay. Thank you. Okay. So please, let's have a short break and then we come back. We go into the survey data within the next 30 minutes. So see you. Right, see you. So I'm going to use a do file. I didn't want to use a do file so I could show you how to do everything manually. Because sometimes people don't like the codes and all those things. Now, you've collected your data. The first thing you have to do when you've got your data into STATA is to tell STATA that this is a survey data, like the way we did for time series, panel data, and all those things. So you go to statistics, you come to survey data analysis, setup and utilities, declare as survey data, and then you choose your sample. So here, oh, I've not imported my data. Sorry. Okay, so let me import this data and we try with this. Okay, so we have our data here, and then this is our ID representing every individual respondent we interviewed. So we go to statistics, survey data analysis, setup and utilities, declare survey data, and then you choose the ID or the sampling unit variable. And once it is done, you just click OK. So we have survey data. So whatever command we do, if we add SDY, the STATA would know that this is a survey analysis, and then it will calculate the population, the sample, and all those things. So from last week, I think that one should be a bit clearer. Now let's go into it. Assuming my dependent variable is binary, yes, no, male, female, what can I do? You cannot run a regression model. So this time around, you run what we called a binary dependent kind of model. So you can choose either a probit, a tobit, and you should be able to go. So now let's go to statistics, and then we go to survey data analysis. And here you see we have binary outcomes. From the binary outcomes, we know that our dependent variable has to be just 2 entries. So let me quickly browse. Where do you study by now? I'm not ignoring it though, but I just want to finish and then we come back to that. So sorry for that. So let's browse the data. And once we browse our data, you realize that there are some entities. For instance, here, how to ensure is just 0101010 binary data. This is also a form of binary data. And this one is also 101010, which is a form of a binary data. And this is the one I've assigned a labels to it, making it a categorical. And it helps when you are conducting some graphs and all those things. So this is an example of a binary data. Now, you can also have other variables called categorical or ordered, those kind of data also. For instance, you want to know level of education. Level of education, if someone is basic education, you know his rank is lower. And if someone is secondary school, his rank is higher. Someone is university, his rank is higher. So that one, you begin to look at what we call ordered regression. There is an orderliness, or higher, lower, and going up. Or maybe when your data is that of the liked scale, like, dislike, extremely like, and all those things, then you'll be looking at ordered. Sometimes your variable, dependent variable, is not ordered, but then it has more than 2 entries. Then you are also going to another form of analysis. It's not binary and it is not ordered regression. But then you go with the categorical variable, which makes ways for more than 2 entries. So with this said, I've showed you some of the variables in the data, and I think it's okay if I close it and we go. Now, this is it. So we begin by explaining binary variables. So when we look at this one, insured, we realize it was binary, 1, 2. So I'm trying to find out if people even buy insurance at all. So to prove that, let's see here, insured. And it is binary, adopt, non-adopt, adopt, non-adopt, adopt, non-adopt. So that is it. So from here, I can decide to run a binary dependence analysis, and you can decide to run a probability or a logic, as I said. So instead of the command, let's go to the interface. So statistics, survey data analysis, and we go to binary outcome. And here I begin with a probability regression, because I don't know if my data has heteroscedasticity or not, or any other thing. So the basic of it is we go for probability regression. We select our dependent variable, which is if the person has insurance or not, and then we select our independent variables. Maybe we can pick whether the real income of the person, and whether the person trusts the financial sector, some of these things, and then we click on OK. Now, as you can see, the model itself is probit, the dependent variable, and then the independent variables. And then this is the output. Last week, Doctor was trying to explain some of these things. When it comes to binary models like this, you do not explain it like the way you explain a regression. You explain it as marginal. So instead of saying that a one unit change in have NHIS has a positive 1.4 effect on adopting insurance, you cannot do that. You can only say that people who have NHIS are maybe 1.4% more likely to adopt insurance. So this is how you run a probit regression, as it is. Now, when you think, please, if you have questions, you can draw my attention because we have limited time. Any question? Okay. Now, the same way you can go ahead and then you run a logistic regression, and mostly the results is going to be very similar with slight difference, because the logistic and then the probit, it has to do with the distribution, the tail, which is not really, really important here. So let's go to statistics, and then we go to survey data analysis, we go to binary, and then we choose logistic. So logistic regression, reporting coefficients, I'm not even sure. And here, you can also choose your dependent variable. We have NHIS, and then the independent variables we use for the probit is, oh, it was insured have NHIS. Okay, so insured and have NHIS and the other variables, and then we click on OK. Sorry, I think the variable ID NHI is not found. I made a mistake in the variable name. Sorry for that. So let's go survey data analysis. We go to binary, and then we go to logistics, and let's see where the mistake is. Oh, I added ID here. Oh. Okay, so why not clean everything and then just paste? have NHIS, real income, and all this. Okay, so submit. Okay, so it worked. Now this is the results, and as you can see, it is very similar to what we have for the probit. It will just be slight difference in the coefficient and all those things. So this is how you perform a binary regression analysis. Here you can also decide to go for IV. You can decide to add IV to it. And in adding an IV, if you think your model has endogeneity, for instance, even though I'm using these three variables to explain adoption of insurance, there are other unobserved variables I cannot explain. There are other unobserved variables I cannot explain. That is when you bring in an IV variable. So let's say have NHIs. I want to say that it's the IV for that. It's more like if the person trusts the financial system, then the person is going to adopt NHIs. So you can go ahead and do all those things. Please, any question on the binary? Please, any question? Okay, so since we've done, let me switch to the DOFA, and I think it will be easier going through the DOFA and we'll be faster, cover most of the things. So if you look at the DOFA I have here, I have a lot of survey models here. I have a Tobit model, and we use Tobit model when our dependent variable is continuous. Mostly is between 0 to 1, maybe 0.1, 0.3, those kind of variables up to 1. But then I have also seen people using it for even continuous variables like log of income and other things. So for here, I am trying to explain the effect of having insurance on income. So since income is a continuous variable, I cannot use probit or Tobit. I cannot use probit or logit. So I have to use a Tobit. So I type Tobit, and then I put my dependent variable and then my independent variable. And I have specified for robust standard errors. So when I choose this and then I run it, this is my Tobit results. Please, any question with using this? Any question, please?
Sorry.
Not really.
Hello?
Okay, so let's go ahead. Now,
Hello?
let's assume that, hello? Okay.
How about if the
Let's
dependent
assume,
variable is not a continuous? Do we still use Tobit?
no, if the dependent variable is not continuous, but it is binary, yes, no, like
Yes.
just 0 and 1, yes or no, maybe male, female, then you have to use either a probit or a logit, which we just did some estimation. I did the probit here. These are just the logit, and this is the probit. This is the probit. So we have probit here. This is the difference. This is probit, and then your dependent, independent. And this is logit, your dependent and independent variables.
Sorry, once again. So to conclude, what determines whether to use the dependent, whether to use probit, logit, and the Tobit is the nature of the dependent variable.
So you use probit, dependent variable is binary. It is taking just 2 entries. Please, did you get that?
Yes, yes.
Yes. And then you go ahead and use Tobit if your dependent variable, it's not binary, but then it's a continuous variable. The best way to use Tobit is if your dependent variable is between 0 and 1. Not like 0, 1, 0, 1, but like 0.1, 0.01, maybe 0.35, 0.99, those kind of things. Then it's best to use Tobit. However, as I stated, I have seen people using Tobit for even very basic continuous variables where it is like 1.3, 2 point something, and all those things. So use TOBIT if your dependent variable is a continuous variable. Use probit and logit if your dependent variables are categorical and then they are binary. Please, is it
Dr.
okay?
Kwame.
My name is just Kwame. Yeah, hello, senior.
Oh, I'm saying maybe for like my case, in case when I'm now trying to access the impact of the credit access on the technology adoption, which model will I use?
Impact of technology access. What?
I'm saying credit access on the technology adoption.
Access.
Yeah.
Okay,
will I
so
use
we have
TOBIT?
credit access. Okay, so let's take it one at a time. The credit access is binary, yes or no, when someone has credit, right?
Yes, but maybe I need to know the extent of the, maybe somebody can decide to borrow some amount, but so I was trying to see that extent. How will I measure that this person can need this amount of credit?
Okay, what is your dependent variable?
Technology adoption.
Technology adoption. How are you measuring the technology adoption? Is it fintech index?
I was trying to ask you now.
Oh, possible. This question is impossible. So let's assume you are using fintech, the index of fintech or financial development, okay, as the variable. Now, for financial development or fintech, it's not binary 0101. It's an index. In some year it will be 0.1 something, some year it will be like 0.3. So that one, even if you are going to use a survey data, then you are going to use what we just did, the TOBIT model.
Okay.
Yes. Now, when you do the TOBIT model, this is the basic TOBIT model we just did. You can go ahead and then introduce an instrumental variable to address for endogeneity. So this time around, instead of typing just TOBIT, you type IV TOBIT. So this time around, it will not be just TOBIT, but rather it will be IV TOBIT. And then your dependent variable, which in this case, we are measuring income. So in your case, it would have been the whether fintech or financial development, whatever variable you are using. So let's assume, where is my income? Log of income. Okay, let me search for it. So in this case, yours is going to be, let's say, the financial development variable, and then your credit accessibility, if an individual borrows from the bank. But your credit accessibility, since you are saying that there is a possibility of endogeneity, you put that one into a bracket, you put that one into a bracket, and then you put your credit accessibility variable, which in my case, it's being insured, and then you put equal to the instrumental variable. So in my case, let's say my instrumental variable is have NHIS, then you close your bracket, and then you add the other explanatory variables. The other explanatory variables, which will probably like the income of the people, the age of the people, and all those things. Please, is it clear?
Okay.
Yes. So maybe I add like age and yeah, I'm not sure which ones has, and maybe an asset level, and then you hit enter. Oh, must specify century point. Okay. So here I'm supposed to specify the century point. So example I have here is this. My IV TOBIT model, the log of income, my explanatory variables, and this is my main variable I'm trying to explain, and this is the IV variable, savings. And then I specify the VCE robust check. I'm using VCE robust, so I can run this. And then I have my results. So I have been able to explain maybe financial development or fintech using access to credit. This is access to credit. And then I also said that the IV for access to credit is savings. So I'll be able to have this. So this is my wild test for exogeneity of my IV model I use, which is not significant, which is a good thing. Please, is this okay?
Yeah, it is okay.
Okay, thank you. So we've done the TOBIT. The same way we can do for the PROBIT. The PROBIT, we can include an IV, which is the same thing. You just add an IV before the model. So it's going to be IV PROBIT. And I think I came with some examples also. I have other TOBIT models here. I think maybe I'll share this. So here too, we have PROBIT, and all those things. So I can run my PROBIT. So please, do you understand the PROBIT and then the TOBIT models? Okay, that is a question. I am trying to estimate building demolition waste. Which of these models is best suited? Please, it depends on how you are measuring your variable. Is your variable survey data or data you collected time series data? Okay. 2, if it's a survey data, the building demolition waste, is it in index form? Is it in numbers? If it is numbers and it's collected over a period of time, then you should be looking at either a time series regression or panel, those things. But if it is an index and other things, then you should be looking at a TOBIT model. You should be looking at a TOBIT model. You cannot use PROBIT, you cannot use logic, because that one deals with binary. Please, is it okay? Okay. Now, I have estimated my TOBIT and my IV and all those things. So I've been able to estimate the effect of being insured on income levels. But this is giving me the effect of insurance on income level. I can go ahead and estimate what we call the treatment effect. In short, T effect. You can go ahead and estimate the T effect. And to estimate the T effect, let me bring my DUFA. The T effect, there are types of T effect. There is near neighbors matching technique. There is propensity score matching technique. There is inverse probability weight technique, and all these things. So all of them have a way of specifying them. So let's look at it. We have help, T effect, and this is it. We have the augmented inverse probability weighting. I didn't even include that. So this is how it is. You can choose the one you want. If you want the near neighbors matching, you start with T effect, the model name, near neighbor matching, and then you specify your variables, and that is it. So example is what I have here. So I can estimate the near neighbors effect. And if you look at the near neighbors effect, you can also estimate the average treatment effect, the average treatment effect on treated. These are some of the things. You choose the particular effect you want to estimate at the end of your model with a comma. Now, when you look at near neighbors matching, you begin with the explanatory variables, and then you bring the dependent variable at the end. But when you look at the PS propensity score matching, you first bring the dependent variable in a bracket, then you bring the explanatory variables. So let me estimate some and show you. Estimate TE and TTE for near neighbors. Okay. So as you can see, this is my average treatment effect. So on a whole, adopting insurance alone has a positive significant effect on the income levels. But the ATT estimates the effect on the people who adopted the policy. So it controls for more like a spill effect. And that is why we have here the AT, which is the average treatment effect on the treated. So here we are estimating for only those who adopted the policy. But here we are estimating for the overall adoption of the policy. There is a very simple thing we have for economics. I'm trying to get it, but it's not coming. More like externalities. let's assume there is vaccination, okay? If somebody gets the policy, if somebody gets vaccinated, we can measure the effect of the vaccine on the person's maybe quality of life. But when more people also get vaccinated, we will have an effect of vaccination on the entire community. Because when more people get vaccinated, it's going to reduce the chances of those who are not vaccinated from catching the disease. Hello? Hello? I thought you were saying something.
Yeah, that concept is herd immunity.
Yes, yeah, more like herd immunity when it comes to vaccination. And in basic economics, we have like externalities, the positive ones and all those. So that is the best way to explain the average treatment effect and then the average treatment effect on the treated. So this has to do with only those who adopted the policy. In our brother's case, this is going to be the people who accepted the credit, the effect on their, maybe their income or their life. But here it's going to be just giving credit in the community, its effect. And please, is that clear? You can go ahead and
explain again.
Okay. There is an average treatment effect and an average treatment effect on the treated. On the treated, we are only focusing on me taking the policy or taking the credit facility, the effect it is having on my income. And then there is an overall average effect of introducing credit in society. So the ATE is the general average effect. And then there is average treatment effect on the treated, which is only the people who accepted the policy.
Okay.
Unfortunately, I wanted to go deep into this whole propensity score matching and the move stay for endogenous switch regression, but time is up. I will just go through. And here too, we estimated for the near neighbors matching. And here the technique is that the model matches those who pick the policy to the closest individual who did not pick the policy. But then we also go to propensity score matching, and we can also estimate for average treatment effect and average treated effect. And it's the same thing. So as you can see, when we use propensity score matching, it is not significant. And when we use near neighbors matching, it is significant. And that is why people will use different models and then they'll pick the one that is significant. So here I will argue that if I should use propensity score matching and near neighbors matching, I'll argue that although my near neighbors matching has a significant positive effect on both the treated and the ATE, however, when it comes to propensity score matching, the effect is not significant. The average effect is not significant. And at best, I will not even report the propensity score matching. Then I'll just save myself from making some long argument. So we can go here. The next thing is there is also another propensity score matching technique called PS Match 2. The PS Match 2 is very good because it can even create your table of balance for you, and then you'll be able to see it. So this is my table of balance. And as you can see, I have my raw data, the matched, and then the unmatched. So before and after standardization. Sometimes some people will ask you to produce the covariate balancing summary statistics. So you know that how before applying propensity score matching and after applying the matching technique. So this is some of the things. You can put it in your appendix. But you can also come here and then you have it in the form of a density graph. So this is it. Now, this is the raw model, and this is the matching. One good thing before you do an average treatment effect is that the matching technique should reduce the difference between adopters and non-adopters. You see, the blue represents non-adopters, and then the red represents adopters. Before matching, there was a big difference between adopters and non-adopters. But after imposing a matching technique, we realized that the gap has been closed for some part, but here it is widened. However, you can go ahead and argue that overall, the matching technique has improved the model to some extent. And that is the reason why people prefer using a matching technique when you are conducting average treatment effects. Because of time, I just want to go ahead and just run the PS Match 2 model. I think I've already defined this. Let me drop this times P-score. Oh, my score already defined again. I have already saved those models, so it's just telling me I've already done that. So where is my P-score? No, I don't even have it saved. Oh, it's here. My score is saved. Yeah. Yeah. And then I can come back and run my model. And as you can see, this is another matching technique. I am matching the treated, which is this red one, and then the untreated, which is the blue one. When you look at this side, I've been able to match for majority of the data, which means when I estimate an average effect, it is better. Propensity score matching is improving the model. And that is why people use propensity score matching and all those things. I promise we will not go beyond 6, so I might end here. Any question? And sorry I couldn't go deep into the survey data today too. And this is the impulse response function in the estimator.
Yes, can I just ask a question?
No. Yes, please, you can ask your question.
Yes, can you go to data browser so I can see
Data
how
browser?
Yeah, data browser.
Yes, please.
Okay, so thank you. So now on the data, let's say this area here, I think we have different areas. And then
which one? The area column.
Yeah, the area column. And also we
Okay.
have how to ensure something like that, I think so. Let's
Yeah.
say you want to see people who have insured according to the areas. How do you do that on a
Okay.
graph? Can you do that maybe on a bar or something? Is it possible to do that?
Yes, that is when you graph and then use the by command in your graph.
To show different categories,
I think
not just
yes. Yeah, I sent a video on that extensively. I think I've shared a video on that extensively. Like, even if you want to graph something, you just use the by here. So for instance, let's say I want to graph by insured. Let's say I want to graph sex. I want to graph sex. And then the main graph I want to do is, let's say, insured. Okay, and I click. So you see, I have this for non-adopters and this is for adopters. So you can do that using the by command, the by option here. And mind you, you can go ahead. Okay.
I didn't see the steps. How did you go there?
Oh, just go to graphics and you choose whatever graph you have you want to do.
Okay.
And then you impose the by. You just have to impose the by.
Okay, I see.
Okay.
Thank you. Thank you.
Professor Kwame.
Oh, Chairman. Shut down or what?
I was proposing, because this is the last lecture, and if there is anything that you have not touched, and we could have wished you to explain, can you just go ahead and do it so that when we wrap up, we have a full video that has a recap of everything that you wanted to present?
Okay, so even if you look at the time series, the panel, I have left a lot of things we intended to cover today because we realized time and we had to go slower. So this, I think we can spend some few minutes and finish, but I actually promised some people will close at 6. Anyway, let's go. So we've done for the PS Match 2. All of them are the same. This time around, the PS Match 2 here, it's estimating the propensity score matching. Okay. Now we can also, under the PS Match 2, we can also choose another technique, which is the near neighbors matching. So here you see, this is I include my neighbor. This is the model I'm using. And then the near neighbor within the 3 neighbors. And then I also use the radius model. It is all the same. All will give you the average treatment effect, on the treated and all those things. But the good thing is, if you use more models to do that, then it's more like you are robusting one findings using another model, like I explained in the panel in time series. For instance, if my study title is Impact of Insurance on Income, Propensity Score Matching Analysis, I will estimate the Tobit model. I will estimate the Tobit IV to control for endogeneity. Then I will go ahead and then impose a matching technique. And then I will estimate the propensity score matching, which is my main model. Then I can go ahead and estimate for near neighbors matching, radius matching as surplus or like as an extra form of analysis for robust checking. Please, is this one clear?
Yeah, it is clear.
Okay. So this is the propensity score matching. Now there is another thing people will ask you to estimate the average treated untreated. This is when you try to assume those who did not accept the policy are rather those who adopted the policy. And those who adopted are rather those who did not adopt. So this time around, you just generate a variable whereby those who accepted the policy would rather be 0 and those who did not accept the policy would rather be 1. You can do this one very easily in Excel using the if command. Do you get it? Hello?
Hello.
You know, sometimes when you estimate the propensity score matching, some people will tell you, have a counterfactual analysis, assuming those who did not accept the policy as those who accepted the policy. And then those who accepted the policy are those who did not accept the policy. When you do that, you are trying to see if indeed the average effect you are getting is from accepting the policy. So you have to assume that those who accepted the policy this time around did not accept the policy. It's like you creating a fake adoption policy, adoption kind of variable, and then you use that one for your regression. Now, when you look at, let me browse and then maybe you'll see BR. I'm not sure if I saved the variable. No, I think I didn't save it. So this is the insured. I'm coming, let me find it. Okay, so this is where I generated the variable in STATA. So I am generating that those who did not accept the policy are rather this. So let me just generate it in STATA. Okay. Now, when I browse insured and then the no insured, as you can see here, non-adopter is 1. Non-adopter is 1. And then insured is 1 here. If you look at this place, you see the value here is 0, which means that for the original data, respondent 1 did not accept insurance. but I am creating an assumption, assuming that he accepted the policy. So you see, I've assigned him 1 here. So I'll use that one for what we call the average treated effect on the untreated. Please, is this clear or confusing? Hello? Hello?
Hello.
Yeah, is this confusing?
Not really, Bobby. Can you just show it again?
Okay. I'm going to go over it again. Now, let me drop the variable. Okay. I am going to generate a variable, which is saying that let's generate no insurance, okay, to be equal to not insured, okay? No insurance is equal to not, which is the exclamation mark, and then my variable, which is the insured one. Okay. Why double equal to sign? Okay, now I have turned the insured variable upside down. So this time around, the people who adopted the policy and we assigned them 1, I am rather assigning them 0. It's me assuming that they adopted the insurance policy so that I can run the average treatment effect on the untreated. So when I browse my insured and the no insurance variable, you realize that they are going to be the opposite of each other, the insured, and then they are going to be the opposite of each other. Now here, okay, let me add a label to it, and I think that one will make it easier for us. Let me just go and add a label to this variable. So value label, and let's put insured. Okay, so when I come and then I browse this, no insurance, and then I choose this. Okay, so this is the original variable. This particular respondent 1 did not adopt insurance, but I am creating an assumption that he adopted insurance for a counterfactual analysis. So when they ask you to estimate the average treated on the untreated, you assume that the untreated adopted the policy. So every variable you see here is going to be the opposite of what is here. If here is non-adopter, here will be adopter. And if here is adopter, here is going to be non-adopter. And that will help me estimate the average treated effect on the untreated. Apart from generating the variable, all the equations are going to be the same, just that wherever you see the insured one, you put the non-insured. So this is it. So you see this time around, I'm using the no insured as the dependent variable, and then I'm estimating it. So when you look at the PS match 2 here, if it gives you the opposite, no insurance, if it gives you the opposite, then you know that, okay, let me just copy and just come and put the right variable name here. Okay, so if after estimating, you see this is the average treated on untreated, and this is the average treatment effect, this is the average treated untreated. So when it comes here, I know that the average treated effect is this, then the average treated on untreated is 0.25. So this is when they adopted the policy. The effect is 0.48. But if they do not accept the policy, the effect is 0.25. Assuming that they did not accept the policy, they would have only gotten a 0.25. So when I subtract these two, I know that those who adopted the policy have more effect or benefit compared to those who did not accept the policy. And this is where you have the difference. Please, is it okay? Hello? Hello?
Yes, yes, yes.
Yes, yes, yes.
Okay, so let's assume it's okay.
Yes, yes, we are there.
Yeah, the video will be available. You can go over it. I think I should have started with this, so it's going to take more time to understand this. But I think I should be able to share my do file. But for the data, it's not possible because it's still a work in progress. So I'm just working on it now.
I have a
And
problem.
you said?
I have a problem.
Okay.
Actually, for this, I think we are examining the impact of a given intervention
Yes.
on maybe on people. But we are using the qualitative, I think qualitative data. So if we are dealing with the quantitative and we are examining the impact of a given intervention on people or countries, so which we shall also use a PCM or PCM is also possible for quantitative or what can we say?
This is quantitative analysis. If you are doing qualitative, you just draw the graphs and then you just go simply like saying 10% of the people, like you do a pie chart and you say 20% are male, 50% are female, those kind of things. Using PSM is pure quantitative.
It is also even okay.
It's the fact that it's like categorical variable, and then I have labeled it insured, not insured. You realize I have assigned value 1, 2, and this is a whole econometric movement we are doing here.
Yes, already they become quantitative.
Yeah, so it's quantitative and it's a bit, yeah, it's hard. That's why, like, even the explanation here, it will take some time. But once you begin to work with it, you would be fine.
Yeah,
Okay.
I have another question, but maybe I can ask it after, or you are going to end the session. It is about about panel. May I ask it? Because maybe you are about to end the session, I think.
Okay, so if you asked it, then meaning we draw an end to it, because this is the endogenous switch regression, which I think, yeah, when you see the do file, you should be able to do it. So, yeah, I'll be able to share my do file with you. Just taking some things off, and then I'll be able to share it with you. So, yeah, you can ask your question, then we draw the curtains to like that.
Yes, yes. You have said an issue of a number of units and the number of units and the time.
Yes.
When we are using a two-stage least squares, the number of units must be also greater than the period, or greater than the time when you are using the two-stage. Because you said that
two-stage regression. Sorry, but two-stage regression is more like ordinary least square regression.
Yes, I
Two-stage
know.
regression is more like the rep command. So these things do not apply. The panel thing to know there is cross-sectional dependency and all those things will not apply. So the years and then the n will not apply, because in two-stage regression, you don't even have n. Everything is just normal regression.
Means there's no problem if the number of units is greater than the number of period. What can you say on that?
No,
number of countries, and you can use it however it can be in any way.
Yes. The reason is in two-stage least square, it's more like OLS regression. So the whole cross-sectional is taken off.
Yeah, okay. All right.
So it's just like two-stage least square is like you have an IV. You've gotten an IV, an instrumental variable to control for endogeneity, and you're introducing it into your model.
Okay.
Any other question, please? We can take maybe one last question and then we hand over to the UIB ASA team. Hello. Okay, so I think there is no other question. And on my side, thank you so much for joining us. It's 5 weeks of, yeah, it's 5 weeks. And thank you for staying around. We appreciate it. For the certificates, we would close the form and then we can confirm the payments and we will let them get the certificates done. So please give us some time on the certificates, 2 weeks, maybe it will appear in your mail. If you chose the PDF, we will email it to you directly. For those who chose the physical one, we will contact you and see how best we can get it to you. Because the address section, we ask that people enter Chinese address. We still have people entering just the name of their university, like Henan University. So, which means we cannot send it. So, another thing. And I'll communicate with Russell and see how far or how best he can handle it. So, Nancy. Hello, Nancy. Hello, Nancy.
Yes, Kwame.
Yes, please, you have the floor. So I've handed over to the UIB ASA team.
Okay. Thank you, Kwame, for the opportunity that I speak. Hello, everyone.
Hello.
I think,
Hello, Secretary.
yes.
Hello.
Hi. Okay. This has been a good 5 weeks, is it?
Yes.
And we are glad that when we asked you to patronize the event and we asked you to come to join the meetings, you patronized them. This wouldn't have been possible without you. We are thankful that you patronized the event, you joined the meetings, and the professors, when they came and they taught us, you were there. And thank you so much. From UIBE ASA executive, and on behalf of the organizers, I would like to thank each and every one of you for being there and for patronizing this event. And to the professors that were coming each and every week, sacrificing their time to come and teach us, I would like to thank you deeply for what you've done. We are full of gratitude because you allowed to attend the event and to teach us throughout this training, and we don't take it for granted. We are really grateful. And from UIBE ASA, we are thankful for what you've done to us and for the whole people, for the whole community, the African community, or the other people that joined in. We are so grateful for that. So mine is just a thank you for each and every single thing that you've done for us and for joining the event, for patronizing it. And Kwame, I thank you as well.
Oh, thank you so much.
Thank you so much.
Thank you so much, Nancy.
Okay. Thank you so much for organizing this thing. I think it has been of benefit to every one of us, and it's been a good 5 weeks. So thank you so much.
Thank you. Thank you.